Hello once again and welcome to our presentation on continuous 2D systems.
You're not the boss of me now. You're not the boss of me now. You're not the boss of me now, and you're not so big. Life is unfair.
Our group was given a continuous 2D system that looks like this. These two graphs are representations of the same system, where the top graph displays our system in the form of a phase plane with these arrows, and the bottom graph merely plots the nullclines with the y nullcline here and the x nullcline here and their intersections. The analytical information we were given about our system is that it is generated by the following two differential equations, x dot of t and y dot of t. In our first task, we're going to analytically determine the nullclines of this system. Second, we are going to infer all fixed points using the nullclines. And third, we will answer the question of how many fixed points a 2D system could have. So let us now determine the nullclines of the system. As you know, a nullcline is a line that is composed of all the points for which one of the derivatives is 0. So to get the nullclines of the differential equations, we must set x dot of t and y dot of t to 0. Then we solve for the variable, and then we plug in the other differential equation to match it to 0. If one of the factors in our differential equation is 0, we know that the entire equation is 0 as well. Let us consider our example. So this is our first differential equation that we set to 0. As you can already see, we have two factors here, this one and this one. So we split them up and set the first factor to 0, because we know that everything multiplied with 0 is 0, and the second factor to 0. Some simple addition with x of t and y of t lets us come to this equation. X of t plus y of t equals 2. These equations in bold are now our x nullclines. To get the y nullclines, we also split the two factors of the other differential equation up into two parts. We can set y of t equal to 0 because we know that everything multiplied with 0 is 0. For the second factor, again, we must do a little addition. We add 1 to come to this equation, x of t equals 1. So now we have 4 nullclines. We have 2 x nullclines and we have 2 y nullclines, all highlighted in bold. Our first task is done. We have analytically determined all nullclines. Now we'll go on to the second task, which is determining the fixed points based on our nullclines. We know that the fixed points of a system of differential equations are located where the x and y nullclines intersect. We can graphically see this by plotting all the nullclines and just checking where they intersect. But we can also do it analytically by calculating the coordinates of the intersections. We will do this now. As you will remember, these are the nullclines we calculated before. And now we will calculate these fixed points. One of these fixed points we can take directly from our nullclines. This 0 we'll get from x of t equals 0. This 0 we get from y of t equals 0. So now we've calculated this intersection. For the rest of the fixed points, we must do some calculations. What we do is we plug the nullclines that aren't equations, so y of t equals 0, or x of t equals 1, or x of t equals 0, into the nullcline which is an equation. So we calculated the fixed point 2, 0 by plugging y of t into this equation. We then solve it and get x of t equals 2. So we plug in the 2 here, and the 0 we got from this y of t. The next and final fixed point we calculate by plugging in x of t equals 1 into the equation and subtracting by 1, thus concluding y of t equals 1. So y is 1 and x is 1 as well. Now we have all fixed points. Note that since the x nullcline x of t equals 0 and the y nullcline x of t equals 1 don't intersect, there is no fixed point between the two. So to briefly recap, these are the nullclines that we calculated. This nullcline is represented on the graph right here. x of t equals 0 is obviously represented right here, y of t equals 0 is shown here, and x of t equals 1 is shown here. We then calculated the fixed points. But as you can see, the null-clines and fixed points we calculated exactly match the null-clines and fixed points visible in the phase plane. These two are the x null-clines, so they denote the set of points where the vector field changes its vertical direction. So as you can see, the arrows are all vertical on these lines. And these are the y null-clines, which denote the set of points where the vector field changes its horizontal direction. The arrows are all horizontal. Now let us divert our attention to the third and final question, which asked how many fixed points a 2D system could have in general. As we saw in the previous slides, the system had as many fixed points as there were intersections of the null-clines. There can be infinitely many intersections of the null-clines, which automatically means that in general, a system could have infinitely many fixed points. We'll illustrate this in the following example. Suppose we have a system composed of the following two differential equations. The null-clines for this system are plotted in this graph. As you can see, there is an indefinite amount of intersections. This is because of the null-cline minus sinus of x of t equals 0, which we can derive from x dot of t in the same fashion as we did before. Therefore, this system has infinitely many fixed points. And that was our presentation on continuous 2D systems. We thank you for your attention.